So last time we said some general things about, motivation behind the study of conformal field theory. We discussed a little bit, this effective description that allows us to get some idea about phase changes as they relate to spontaneous symmetry breaking. For that, we had to introduce some variable m, some collective variable m, which was this magnetization. Then we promoted that into a function of x. We made it local. And then we even sort of like abstracted out of that and started using some phi of x and wrote down Lagrangians and so on. And we said that because of these ideas of universality, many different systems belong to the same universality class once they reach, the conformal fixed point. And we ended up using this Lagrangian, the epsilon expansion, for example, to get some results for critical exponents in the case of, say, the phase transition of water or the phase transition of the 3D Ising model that we discussed. And then we talked about conformal transformations because, for reasons, of course, I didn't go into the reasons, but except that the fact that the correlation length at the conformal theory becomes infinite means that the theory becomes scale invariant. There are no scales in the theory. The two-point function takes a specific form. And the suggestion in the old days was that, and it's still valid, that, well, most likely this set of scale transformations enhance to the conformal group. You get also these special conformal ones, the ones we discussed at the end of the last lecture. And so people believe rather widely that whenever you have a theory that is unitary and scale invariant, it's also conformal. But, there are some not pathological, but some sort of like esoteric free theory examples where that's not the case. But whenever we have interactions and we find an interacting fixed point that is scale invariant, then it's also, if it's unitary, it's also necessarily conformal in all these cases, although there is no general proof of that, There are various, good arguments in the literature as to why that's the case, but there is no general proof. Anyway, here, in everything I will say from now on, we will assume that whenever we are at a fixed point, we have conformal symmetry, and we can use this to constrain the physics at that fixed point. Okay? Okay, are there any questions from last time? Okay, maybe not. So today, let's start by, once you do this in field theory, of course, once you understand how some transformations act in space, right, then the next thing you need to know is how they act on functions you may define on that space. And functions you may define on that space, you want them to furnish, irreducible representations of the symmetry group of the transformations that you now know how they act on space. So in the case of Lorentz, symmetry, Poincaré symmetry, which is the usual case, we define some function phi of x, let's say, which is a scalar function of x. We know how Lorentz transformations act on x, say send x to lambda times x, and then we say, scalar function is one where that doesn't change under this transformation. But then there are more complicated ones, like spinors. You can define things with space-time indices, vectors, traced symmetric tensors, and so on. And those furnish irreducible representations. They have specified transformation properties. And since they have specified transformation properties, you can use them to build Lagrangians that are supposed to be invariant, and so on. We're going to do the same thing here. But now we have two more transformations. Well, two more sets of transformations, the dilatations and the special conformal transformations that we have to understand how. And we have to understand how those act on functions we define on space-time. Okay, so from so the conformal group, as we discussed last time, you can show is the indefinite orthogonal group SOD, 2, which preserves a quadratic form with two minus signs, okay? Now, in most of what I will say, I will take this and go to Euclidean, where this becomes SOD plus 2, okay, by rotating those minus signs away, multiplying with an I. But sometimes people also discuss this, this group in Minkowski signature, where you go to D plus 1, comma 1. Okay, this gives rise to this embedding space formalism that you may have heard of. We will not talk about it. But there are different ways that that may be useful for different things. As you know, depending on what you want to do, there are different convenient ways to deal with this group of transformations. Okay.
I thought that this was precisely in Lorenz's signature. When it's in this, when it's as D plus 1 1, it's in Euclidean signature.
So this is the indefinite one, right? Where you have two of them.
Yeah, but it's I mean it's a conformal group for Lorenz.
You have two minus signs
in
the indefinite norm, yeah.
Yeah.
And you can go to.
I mean, this is the conformal group for, let's say, d-dimensional Minkowski space.
Yes.
Yes.
But you can go to D plus 1.
Which would be the conformal group for the Euclidean d-dimensional space, right?
I think he's saying that SO D plus 1, comma 1 is the conformal group for
D plus 1. Oh yes, of course, yeah.
So, but here you want to.
I'm saying that.
Rotate, I mean, so you want to do SOD plus 2, but then it's not the conformal group either of.
No, it's not. Yes. It's not. But I can view the transformations in that way as well. Saying that's all. Yeah. I didn't mean to imply that it was. Yeah, I didn't mean that it was a conformal of some space. No.
Okay.
Yeah.
Do we consider only flat space?
Sorry?
Do we consider only flat space time?
Yeah, this is all in flat space time. Yes. Yeah. Okay. So in field theory, you define fields and then you discuss excitations of the fields, particles, and so on, right? Here we don't have this kind of picture because we are supposed to be in a conformal theory. There are no particles because if you have particles, then they have some sort of Compton wavelength, which means that they have some size. But in a conformal field theory, nothing can have a size because that introduces scales. So we will not talk about things as fields, but we will talk about things as operators. Okay, this is the usual discussion. This is the usual terminology used for functions on spacetime. We don't call them fields because there is not this associated picture of excitations of fields from field theory, so we call them operators. Okay, so my notation in general will be that OI of x is an operator. Where x is the point in space-time, d-dimensional space-time, and this I index over here tell me the Lorentz transformation properties of this operator under rotations, okay? So this I is not, it's a collective index. It could be many indices. For example, many space-time indices could be a traceless symmetric of spin L. So this I would be many mu1 up to mu L. So this I is basically basically specifies specifies in some sense the Lorenzi rep, meaning under rotations how the operator behaves. Okay, very good. Now, so what do we want to do now? We want to understand how these operators change when I take my coordinates x, I change them by a conformal transformation g, and I go to x prime. Then there are some operators, OI, that go to some OI prime, such that OI prime at the new point is given by some function omega of x to the power minus delta times some rotation matrix, which is decided based on what irreducible representation of the Lorentz group this operator transforms under, okay, times the operator at the old point. And this is not true for all operators in the theory. This is true for a subset of operators, which we call conformal primaries, okay? So this relation over here is only true if the operator is a primary. There is a trivial way to find operators that are not primaries. If you take a derivative, right, then this derivative of a primary will not be a primary because the derivative by the chain rule will also hit this thing over here. It will generate extra terms. So you can use transformation properties like this to call a bunch of operators primaries, and derivatives of those operators will not be primaries, but will be what we call descendants, okay? Derivatives of primaries are called descendants, okay? Now, I will not prove this, but one can show that if you have unitarity in a conformal field theory, then every operator in the theory can either be a primary or a descendant. Now, sometimes it can be both, okay? But whenever it's both, it has to be set to 0. And this you can see in many different ways. If an operator is both a primary or a descendant, then it satisfies some sort of conservation condition, which sets it to 0. One example is a conserved current in a conformal field theory. If you look at the divergence of a conserved current in a conformal field theory, say you have some global symmetry, some continuous global symmetry and associated conserved current, then the divergence of the current would be a descendant because it's a derivative, but it's also a primary, you can show. It satisfies this relation as well. But the divergence of a current is 0 because the current is conserved, and therefore that state, that operator is sort of removed from the theory, right? And one would say that the terminology would be, so the fact that operators are either primaries or descendants means that you can take a primary and then act with derivative to generate a whole tower of operators that sort of like get sourced from the same primary. That's why they're called descendants. That creates a conformal family of operators. The standard terminology for this is that it's a Verma module, right? And the operators in the Verma module that are both primaries and descendants have to be removed from the module, okay? Very good. So this is, there are different ways to define what a primary operator is. We'll see more later. But anyway, the key point from here is that one can think of operators in a CFT in a way that you don't have it in regular quantum field theory, where you have an operator that's sitting at the bottom of some sort of multiplet, and that multiplet has at its bottom this primary operator, and then all the other operators in the multiplet are generated by acting with derivatives on that primary. Okay? Very good. In that sense, we understand the primaries as the more fundamental operators in the quantum field theory, and now we need to understand how they are constrained by the conformal group. So we will introduce generators of the conformal group. So how do we do this? I mean, just to remind you, whenever we have, the generator of translation. Say, how do you introduce it? You say, well, I'm going to go to x plus epsilon. I will expand this out. You stop at leading order in the infinitesimal change that you made, right? And then you say, let me get the signs right. You say that you're going to call this phi of x plus epsilon mu I p mu phi of x. And this p mu over here is minus I d mu. So the generator of translations is this minus I d mu that you know. Okay? So now you don't have to necessarily have a differential representation of that operator, right? We may now seek some sort of abstract representation of this operator, which I will call non-calligraphic p mu. So this is the p mu operator that acts on the field phi in a commutator. And what it does is it gives us I d mu phi, which is minus p mu phi. Okay? And the minus is important. You cannot avoid it by going to some, other Hermitian or non-Hermitian, whatever, it doesn't matter. You're always going to have that minus. And the minus is because you want these operations to compose in the right way. So let's see what that means. So now that I have, found some sort of abstract p mu whose commutator in the differential representation acts like this, then I can ask if I have two operators, A and B, that act on phi successively. So B acts first and A second. Then I would write this like this. They're all, bosonic operators. And now there's going to be some differential representation of this B operator, right, that it can act on. And I'm going to denote this by, there's going to be a minus sign because I'm going to the differential representation. And now I'm going to call this some B differential. It's like that curly P there on phi. So since this now is in the differential representation, I can pull it out, right? And then apply the same. I'm going to get another sign, and I'm going to get something like BD AD on phi. And so what I found is that these abstract operators, B acts first and then A, but when I go to the differential representation, it's A that acts first and then D and then B. Okay? So if I look at the commutator of the abstract operators A, B, this is equal to this, and this minus sign is consistent with that minus sign over there, okay? Where you can call A comma B, you can call it some other operator C, and then the differential representation of C, you would want to be the same commutator, and then you're forced to have the minus sign. I'm just saying this because you guys are graduate students, so you're supposed to do calculations, and if you try to do calculations with what I'll tell you later, you will see a lot of signs being off unless you account for this sign here, going from the, correct?
Yeah.
Which part?
I made this mistake many times.
Okay. You can make sure you know of this sign. I didn't know, when I was a graduate student, I didn't know about it, and I spent a lot of time being frustrated with this sign. What the hell is happening? And then eventually, I realized that there was an extra sign. And this really has to do with the fact that, you can perform it.
Pride in them of part of their PhD experience.
Yeah, well, okay, I'm saving you maybe a couple of months of frustration. Anyway, it has to do with the fact that when you rotate an operator, you can either rotate the system, of reference, or you can rotate the position of the operator, say, and those are opposite. There is a minus sign. Opposite transformations. One is the transformation G acting on the operator, the other one is G minus 1 acting on the coordinate right? This is the same for Lorentz transformations. You've seen it there. Probably without noticing. Anyway, so it's important. It's an important sign, so keep it in mind, even if you think it's useless now. So, okay, now that we have defined this for P mu, we can go and do exactly the same thing for other operators. Remember, we know how they act on spacetime. We know what they do here. We can expand that out in an infinitesimal form and find the corresponding differential representation for all the different transformations of the conformal group. Now, once you do this, you get the following equations. Let me just write them down.
Sorry.
Yes.
Regarding this minus sign, is it because when we define this, how AB acts on P, we get that they kind of switch their places?
Yes, it's because once I go to the differential representation, B acting on phi, this commutator means that I'm going to get just this. And now this is just a differential operator. I can pull it out, right? And I have to now define how A acts on phi, which is this AD. So they end up in the opposite order than they started when you go to the differential representation. And it's important that they end up in the opposite order, and you'll see why in a minute.
But if we...
You can't. They have to end up in the opposite order. Yeah.
Sorry, I missed the step where we go from the commutator of B and phi to B to the power of D. Why?
Well, I applied it both times. Like, one commutator is this, the other is this exchanged. But since I get them in the opposite order, I'm going to have the minus sign. If you didn't have that minus sign, you wouldn't be able to get this minus sign, right? And it wouldn't be consistent with that over there, which, we showed. I mean, even in quantum mechanics, if you go to quantum mechanics books, they will tell you that H, P0 is IDT, but the action of P0 on a state is given by minus IDT on the state. It's not, or the other way around, something like that. And that's the same sign. They tell you this, but they don't, sort of make much of a point of it.
The first step, we're assuming that the differential rep of B doesn't act on A, right?
Here.
No, on the right.
Here, yes, exactly.
So the fact that we pull the BD out is because BD doesn't act on A.
Exactly. This is an abstract operator that acts on phi. And this over here is not something that acts on A.
It's true for all operators in the...
Yeah, yes, this is an operator in... this is an abstract thing. This is a differential representation of the operator B. They operate on different spaces in a way, so you can pull it out. Yeah. Because operators compose in opposite ways in the different representations, this is something you have to be careful about. Oh yeah, no, I shouldn't have erased that. So now so I wrote already down that P mu on phi is ID mu phi. Sorry, let's not write it on phi. Let's write it more generally on some primary OI of X. This is it's like that. Now we have dilatations. You can repeat this exercise for dilatations. You know how dilatations act on X. They send it to lambda X with lambda some positive number. So you can write that lambda as, perform this manipulations, and you will find that this is minus I X dot D plus delta and this delta comes from the transformation property of the primary that I erased. Remember, I had this omega of X to the delta, right? You use that omega of X for dilatations, and when you expand it out, you'll get some delta. Okay? Anyway, and you know how Lorentz transformations act, and that's where these are the rotation matrices in the representation under the Lorentz rotations carried by this operator. Okay, if this operator is a spinor, you know they are the commutator of gamma matrices, for example, up to a factor of a quarter maybe. Okay, and finally, special conformal transformations. Special conformal transformations act in a more complicated way. X. Okay. So these are the transformation properties of the operators under the action of the generators of the conformal group. And I wrote them because I'm pretty sure the signs are all correct, which they are usually not in the literature. Okay. So to see now look at this over here. Remember this we said is an operator OI that is a primary. If I take this operator OI to sit at the origin, x equal to 0, then this whole right hand side is 0. Okay? So an operator that's a primary is annihilated by k mu when inserted at the origin. Okay? And now you can see also why the order reversal is important that you guys were asking about earlier. So let's see why the order reversal is important. If I were to take a primary operator, let's call it phi, and I were to compute this commutator over here, right? Then, if the operator is a primary, I better get 0, right? Because at x equal to 0, I'll get 0. Now, suppose I wanted to do this in the differential representation. Now, what would you write?
Why should we expect 0? Sorry?
Because I said that this phi is a primary, and this is, you know, you put it, there's x here, x here, x here, and x there. So if you set x equal to 0, you get 0. Rather trivially, and this is another way to call an operator a primary. It's annihilated by k mu when is inserted at the origin. Okay, so if this is at 0. So for a primary phi, I better get this. So now there are two things you can write. You can write p mu differential, k nu differential on phi at 0, or k nu differential, p mu differential on phi at 0. Now, which one of these is correct? Now this is an operator, and the issue is that the differential representation of this has x's. Okay, and has a piece here that's linear in x. So if I let this operator take the derivative here, I'm going to lose the x. Okay, and then I'm going to get something non-zero. Okay? You see? And therefore, you cannot let the operators act in the same order. This is the correct one, because you will see from here, you will just get some k nu differential I d mu on phi of 0. Okay, well, phi I d mu and phi of 0 is still at 0. And this differential representation of this, doesn't care. It will choose this x to be that same one. And it will not change the fact, despite the fact that this is not a primary, will not change the fact that you will still get 0 here. Okay, so you see that the order in which the operators compose into the two pictures has to be reversed in order to be consistent. Yes?
Are these transformations only acting on primaries?
Yes.
So how can K act on, how do you know K acts in the same way on the descendant?
Well, it doesn't matter. It doesn't matter if when the descendant is inserted at the origin here, you can work out what its transformation is, putting the derivative in, right, and working it out, using the commutator of K mu with P mu that I will write down and so on, and you will see still that you get 0. But yes, you have to do all this. I haven't told you what the commutator is, but I will now. Questions? Yes.
Can you say something about the unitarity of this transformation?
What unitarity?
Well,
Oh,
these operators like permission. Yeah.
Oh, well, I don't want to get. That's a tricky issue. So I don't want to. Yeah. So yeah, let's not discuss this now, but maybe we can discuss it later. But I don't want to get into that now. Yeah. You know, defining conjugation and all that stuff, we'll see when we do radial quantization today how tricky this can get. And okay, let's not get into it now. But it's a very good question. And therefore I will dismiss it. Okay. Very good. Thank you. And now let's finally write down how these operators, the algebra that these operators satisfy. And this is, there are standard relations that you know from the Lorentz group. So this is one of them. Whatever I don't write down is going to be 0. There is a new one here because there is a non-zero commutator between the generator of rotations and the generator of special conformal transformations that takes a rather similar form. New. Then there is this long one, which, okay, I may write down depending on. D with P mu is I P mu, or minus I P mu rather. D with K mu is I K mu, and K mu with P mu is equal to 2I eta mu nu D and then okay, so these are all the commutators in the algebra. Okay? Okay, very good. Okay, so why did we do all this? Well, why do we worry about operators? Operators are not observables. So who cares? Why do we care so much about what the generators of the symmetry do on operators? Because you can use operators to construct observables, which are the correlation functions, okay? So by knowing how the algebra of the transformations acts on the operators, when we have these correlation functions, we can then use these same equations to see how the algebra acts on correlation functions. And once we know how algebra acts on correlation functions, we'll be able to constrain what those correlation functions will be able to look like, in this case, in a theory with conformal symmetry. So that's what we're going to do next, unless there are any questions. Okay. course, you already use this. For example, in a Lorentz invariant theory, you always say that, suppose you take, for simplicity, let's take take scalars, say phi1 and phi2. These are in general two different scalars, phi1 and phi2, okay? And you're going to say that I want to know what happens if I insert phi1 at x1, phi2 at x2, and I consider this correlation function. What form can this possibly take? Already using Lorentz invariance, you say, oh, because of translations, this right-hand side cannot depend on x1 and x2 separately, but rather only on the difference x1 minus x2, right? This is a direct consequence of the fact that you have those, the things that I erased, that the correlation function has to transform covariantly under the action of the translations in the Lorentz group. So that's one thing. And then you also say that, oh, well, actually it cannot depend on x1 minus x2 vector. It has to depend on the invariant of that vector in the Lorentz group, under rotations in the Lorentz group, which means that it has to depend on the square of that vector, right? So you would write that in general, in a Lorentz invariant theory, there will be some coefficient times some function of x12 squared that this correlation function can depend on where x12 is x1 minus x2. Okay? The vector x12 nu is that. That's how far Lorentz invariance gets you. And now you want to ask, okay, now I have two more. I have d and k mu. What do those do? And in order to sort out what those do, we're going to use the same equations. We're going to say, well, the correlation function must be invariant under the action of dilatations. If it is to be a correlation function in a theory that has conformal invariance, it's going to have scale invariance, and therefore the correlation function must be, of the scalar operators must be invariant. And now what you do is you use that differential representation of the operators that I showed you, that I just erased. It was here. This d acting on phi was something like I x or minus I x dot d plus delta acting on phi, right? And this is an operator inserted at x1, and this is an operator inserted at x2. So when I act this out, I will get d acting here, and then it will go through and act here. So I will have I x1 dot d1, where d1 means the derivative with respect to x1, plus delta 1 plus x2 dot d2 derivative plus delta 2, where delta 1 and delta 2 are the deltas associated with these two operators in the representation of this d operator. And I'll get, after I act, I'll get this thing back, right? So this will be acting now on f of x12 squared, and this must be 0. And this, acting the derivatives out, it turns out to give you something like, you can check the algebra, f prime, where f prime is a derivative with respect to the whole square there, plus delta 1 plus delta 2 f is equal to 0. So you basically get that f prime over f is equal to minus delta 1 plus delta 2 over x12 squared to the 1/2 delta 1 plus delta 2. Sorry. No, that's the final answer. Over x12 squared. And then this is solved. This implies that f is 1 over x12 squared to the delta 1 plus delta 2 over 2. Okay? So in a theory with scale invariance, there is a power law behavior in the 2-point function, and we haven't even used conformal invariance yet.
Should be over 2.
Sorry? Let me see. Here?
Yeah.
What should it be? Over 2? Yeah. Yeah. Very good. And right, so this is what you get when you use scale invariance, and now you can do the same derivatives and so on for k mu, and you will when you demand that the same correlation function is invariant under the action of k mu, you work it out, and what you find in the end is that here I forgot the c somewhere. So there is the c that we put here in the front, or no, actually this f is that without the c. Sorry. So here we have c delta 1 minus delta 2 appears times f is equal to 0. So this is just a little bit more complicated calculation, but it's completely straightforward, just taking derivatives of that form over there. And therefore, in order for this to happen, either c is 0 or delta 1 minus delta 2 is 0. Okay? So if you have a theory that is conformal on top of being scale invariant, then it must be that either c is 0 or delta 1 is equal to delta 2. In other words, two operators that do not have the same dimension in a conformal field theory will necessarily have a 0-2-point function. Okay? So this is the result that you get, and finally you can write that phi 1 at x1, phi 2 at x2 is some coefficient c1, 2, and then the Kronecker delta of delta 1 and delta 2 times this power law. This is the most general form you can have in a conformal field theory for the 2-point function. And this we worked out here for the 2-point function of an operator of these two operators that are scalars. It turns out to be the same for 2-point functions of operators that are not scalars. Okay, they can have any representation under the Lorentz group, and you will still have only an operator with itself, with an operator of the same dimension having the possibility of a non-zero 2-point function. But of course, the form of this 2-point function will be quite a bit more complicated here on the right-hand side, but it will still be a unique fixed form, given in terms of there's going to be some tensor up here that will carry all the indices that those operators will carry will bring in from the left-hand side. So it looks a lot more complicated, but it's actually the point is that it's exactly the same thing, that operators only have a 2-point function with an operator of the same dimension, and then you can use that to work in a basis where an operator will only have a 2-point function with itself or its conjugate, so that you never have to consider operators that are different and discuss their 2-point functions, even if they have the same dimension. Okay, you basically write some matrix of these operators, and basically you work in a basis where you diagonalize that matrix. It's a symmetric matrix, so you will be able to diagonalize it, and then you work in that basis. Okay, very good. So that is what you can say about the 2-point function, and similar but a little more complicated calculations you can do for 3-point functions. Now, for 3-point functions of scalar operators, there is again a unique form you can write down, meaning unique in the sense that the x dependence is fixed. But there will be different numbers appearing, like, here, again, the x dependence is fixed, but we don't know what this delta is. This C12, you could absorb it into the operator, so it doesn't really matter here. But we don't know what this delta is, but we know it's going to take this form. For the 3-point function, there will be a coefficient of scalar operators. There will be a coefficient C123, right? Which you can no longer absorb anywhere. It's actually dynamical and physical. It's called, some people call it the OP coefficient, the Wilson coefficient. It has various names. And then there's going to be delta 1, delta 2, and delta 3. Those are going to be the unknowns, but the x dependence will be fixed just like this. It's just going to be a little bit more complicated. If you have operators with spin, and you consider 3-point functions, there is no longer just one C123. There are many C123s. And that depends on how many structures you can write down that are invariant under the conformal group out of operators with the representations of the Lorentz group you put here. This is not necessarily one structure. For a scalar, it's only one structure, but for operators with spin, it will be more complicated. So there will be more than one C123s, but each one of them will be multiplying something that's completely kinematically fixed. But there will be independent things you can fix kinematically. Okay? And this is because you're just multiplying 3 representations. You have to decompose the product of the representations into irreducible representations again of your group. And this is the reason why you have the possibility of more structures. Okay? And, okay, so, but the point is that whenever you consider 2 or 3 points, everything is fixed basically kinematically. There's no dynamics other than in this number C123s and, you know, the deltas, delta 1, delta 2, delta 3. So, why is this happening? This is happening because if you start with 3 points in space, there is no way to write down something that is conformally invariant. So conformal covariance properties of the correlation function completely fix it. Okay? However, starting at 4 points, you can write down 2 quantities that are conformally invariant. Okay? And you can check that. There are conformal invariants can be found with 4 points or more. In the case of 4 points, so for 4 points in space, you can construct 2 things, usually denoted by U and V. This is x13 squared. And the other one is V. And you can check that these are fully conformally invariant. Okay? And therefore, when you write down 4-point functions, you can no longer expect conformal covariance properties to fix the correlation function kinematically. They will fix some part of it kinematically, and then there will be some overall dependence that on these invariants, U and V, that you cannot fix kinematically. This is an unstable equilibrium here. Okay, so
things get interesting with the formal function.
Yeah, so this is, you know, going to be the first case where we might seek, you know, how the conformal theory, the conformal symmetry, although we have this dependence on U and V that seems completely arbitrary because they are invariants, one might start to think of ways to nevertheless try to determine the 4-point function using various tricks that we will get to in the next lectures. So this seeming dependence on these invariants U and V is actually, you know, illusory in some sense. The 4-point function, you can use things like the operator product expansion and things that we'll get to next time to actually determine it in some sense. And we'll see what that means next time. For the rest of today, we will discuss the setup that we need to introduce in order to get to that operator product expansion and other things, which is radial quantization. But we'll do that after the break, I guess. Unless there are any questions.
Yes, I have one question. So my understanding is that the 2-point function, maybe also the 3-point function, don't depend on the details of the theory, right?
No, they depend very much on the details of the theory.
Assuming conformal symmetry.
They depend very much on the details of the theory because they depend on these numbers, and these numbers are dynamical numbers that we have not determined, but the functional dependence, meaning the dependence on x, is fixed. It's not some arbitrary function of x. It's a particular function of x with some particular exponent delta. These deltas are related to those critical exponents we were discussing last time. And so is the 3-point function. The 3-point function will have coefficients here, C1, 2, 3s. There could be more than one. And then the delta 1 and the delta 2 and the delta 3 of the operators you are involving as external operators in the 3-point function will also appear here in complicated ways. But the x dependence will all be fixed.
Okay.
So that's what I meant. That
and for the 4-point function, instead you have some kind of...
For the 4-point function, I cannot fix the x dependence because there will be an undetermined function of u and v that the conformal transformations will not fix. And this can be any function of u and v in principle. But we'll see that it's not, but it could be any at this stage. Other questions?
No.
Well, you're looking at your phone anyways. All right, let's take a 10-minute break and continue with the next topic. So here we talked about correlation functions. And if you remember, when you discuss correlation functions in field theory and you want to make sense of them, the first thing you need to define is the quantization you're in. And here I didn't pay attention to that, but there turns out to be a reason to consider it in conformal field theory. There is a sort of a convenient quantization that's called radial quantization that I want to discuss now. But let me remind you what you do in field theory. So the Hilbert space construction of QFT basically amounts to choosing a space-time foliation. And there are all sorts of ways to do this. But the convenient way to try to do it is to do it in a way that's sort of consistent with symmetries of the theory. Okay? And that in QFT is usually done by thinking about time evolution. And you use the Hamiltonian to sort of generate that time evolution, right? And so you define hypersurfaces of codimension 1 that this time evolution moves you along, like this, on each of these hypersurfaces. So these are in a d-dimensional QFT. These are d-1 dimensional hypersurfaces, and each of these hypersurfaces has its own Hilbert space. And the Hamiltonian will just take you from one to the other under time evolution. So this is the standard space-time foliation. This is called the equal time foliation that you would do in field theory. Okay. Now, in CFTs, one could do this, but it turns out that there are some things we want to say that are much easier in a different foliation. Okay? And that different foliation gives rise to radial quantization. So instead of talking about things like, equal time commutation relations and so on, we will have this radial quantization, which is a foliation, which corresponds to a foliation by d-1 dimensional spheres of different radii. So here is a point, and we're going to foliate in this way. Okay? This is radial quantization. And in order to this is useful in a CFT because you have a generator of the algebra that moves you from one of these spheres to another. And that generator is the generator of dilatations. If I do dilatations and I change all the coordinates by some lambda that's bigger than 0, basically I can move from one of these spheres to another. And I can also use dilatations to take anything I define on these spheres and squeeze it down to a point. Right? And this turns out to be very convenient for reasons that we will discuss now. Jeez, this is going to fall soon, but okay. So instead of talking about states, so remember we had the Hilbert space foliation, the equal time foliation, and in the Hilbert space we were characterizing states by their energy because we're using the Hamiltonian. So here, instead of using the energy to define states, eigenstates of the energy of the Hamiltonian, here we're going to use eigenstates of the dilatation operator. Okay? So eigenstates of the so the states in this foliation are characterized by the scaling dimension instead of the energy, by that delta. And this delta I will call typically scaling dimension or dimension of the operator, of the state, rather. And I will write equations like this, where d delta is minus I times delta times the state delta. Okay? So eigenstates of the dilatation operator will be the states I define on those spheres. Okay, similar to the states in the Hilbert space that we have in equal time foliation. And there is also, of course, if the states carry some spin, described by this index I that we were using before, then there is also this transformation under the algebra that we need to consider. Okay, so how do we generate states on the spheres? Remember, these are not the Hilbert spaces of our theory. They live on different spheres. And to make this picture, why do we do this? Why is this a convenient picture? Is because of the easy way with which we can generate these states. So how do you generate these states? You generate states by inserting operators inside the spheres. So states on the sphere are generated by inserting operators inside the sphere. And how do you get the vacuum, for example? Vacuum state, you insert nothing. So the sphere. Now since we have the vacuum now, we insert nothing and we call that the vacuum. Now I can imagine that I insert an operator O delta at the origin, okay? And now that will act on the vacuum, and this we will call the state delta. So I have the vacuum, I inserted nothing. When I insert an operator O delta, one of these primary operators O delta at the origin or descendant that we had, then that is the state I call delta. Okay, it's just a name. And what is the energy of that state? I may compute now D on delta to basically reproduce that equation. Well, this is explicitly written like this by definition of what we call the state delta. And now I can act on this O delta by the commutator, and there will be another piece here where this D goes and acts on this state, right? But that's the vacuum state. So D on the vacuum will give 0, so I forget about that piece. So it's just the commutator that survives. And now I use my previous sort of algebra, right, that I wrote before, how this operator acts, and I get this minus I times delta. So this is indeed an eigenstate of, if this O delta is a primary operator, this is an eigenstate of the dilatation operator. Okay? Okay, that's good. And now, since I have inserted an eigenstate, which I did by inserting a primary operator at x equal to 0, I also know how to conjugate the operator with translations and move it around. So I can see what I get if I insert an operator at x, not at 0. So what do you get? So number 3 is inserting O delta at x other than 0. How do we get that? Well, we get that by writing the state that is generated by the insertion of the operator at x other than 0. And that, we know what this O delta of x is. It is e to the I p dot x O delta at 0, e to the minus I p dot x on the vacuum. And this will be just e to the I p dot x, since that's the vacuum. Sorry, on this state delta, basically. Okay? Which we may write also by expanding the exponential as sum over n. Okay, so
what about the second step? Where is it from? We call this delta here.
you get the 1, but it's Lorentz invariant theory, so you get the 1 from here when you expand this. Then P on the vacuum will give you 0 for the rest, so you just keep the 1. And then you get this. And then O delta at 0, oh no, is what I called delta before. And now I just write back the exponential in its form as an expansion. Okay, so what is this now? So inserting an operator at 0, we said is an eigenstate. What is this? So in order to find out what it is, we have to compute D on it. And there was a non-trivial commutator of D with p mu, and there's going to be a lot of p mu's here at the various powers of n, right? So in order to see what the D on this state is, I'm going to have to commute D with all these p's in order to be able to get to this delta where I know what it is, right? And so D, it helps to compute the commutator of D, of how D acts on p mu on delta. And this turns out to be, you guys can work it out, minus I delta plus 1 p mu delta. So this is an eigenstate. P mu delta is an eigenstate of the dilatation operator with eigenvalue delta plus 1. Okay? And if you do it twice, it would be delta plus 2 and so on. So now you know how it's going to go through, what it's going to do when it acts on the product p to the n times times delta. And what we see is that we don't really get an eigenstate, but we get an infinite combination of eigenstates. Because if it acts on the state with 1p, it's going to be the state delta plus 1. And then if it's 2p's, delta plus 2, and so on. So what we get is we include the states delta, and then acting with 1p, we get the state delta plus 1. From this equation over here, with another p, we get the state delta plus 2, and so on. Okay? And for this, we used the fact, in this commutator, we basically use the fact that dp mu is minus I p mu. And this minus I p mu gave us this plus 1 over here, because of this minus I. Now, there is another commutator that we had, that dk mu is plus ik mu. So if I take a state and I act with p mu on it, I get the state with dimension delta plus 1 because of this minus sign. But if I didn't have the minus sign, I would get the state with dimension delta minus 1, right? So p mu sort of raises the dimension of the state and k mu lowers it. So I can start with I can end up in the same delta from the right, like this. So for this commutator allows you to do this. But of course, if I were to lower the dimension of the state indefinitely, then I would have to hit 0. I cannot lower it indefinitely, because then I would go to arbitrarily negative dimensions. And arbitrarily negative dimensions, if you remember the form of the two-point function, means that if I take two-point functions of operators associated with those states, that would be x to some positive power. And if it's x to some positive power, it means the farther away the operators are, the more they interact, which is sort of counterintuitive. And we don't want that. And so we need to put a bound on how far down we want this operator k to go before it stops introducing any new states. So there is a state on which the operator k acts, and it gives us the vacuum. It does not keep going down. Okay? This is basically from requirements of unitarity. So that state on which k acts and gives us the vacuum is again the state associated to the primary operator O. So let's summarize this. So we saw how we can start with an operator and generate a state. You take the operator, you insert it at the origin, and you generate a state. So for every operator, you can write a state. So maybe this is an operator state, correspondence. This is always true, right? You have a vacuum in field theory. You can take an operator, act on the vacuum, and you're going to get some other state, right? So it's not very special here. You have a state, you have an operator. But now we see that in conformal field theories, because of this convenient foliation, you can do it the other way around too. If you have a state, you can get an operator out of it. So this is what we call the operator-state correspondence, that is valid in conformal field theories and is not valid in general quantum field theories in one of the directions. In particular, you can, if you have a state, yes, you can always get, if you have an operator, you can always get a state by acting on the vacuum with that operator, but not the other way around. But in a CFT, it's also the other way around. So, this operator-state correspondence, it goes back to this idea that we have these spheres and we can use the dilatation to take the states defined on a sphere, right, and shrink it down to the origin, and that at the origin we know now it will give us an operator, because we showed that operators inserted at the origin generate states on the sphere. I can shrink those states and get that operator back. So this is what gives you the state to operator map. But if you remember the equal time foliation we did for the QFT, this doesn't really work, because if you tried to go to t equal minus infinity, right, start from a state in the Hilbert space at some hypersurface and go to t minus infinity to generate some sort of operator, then you can do it. You cannot associate it to a point, because the hypersurface is an equal time foliation. You're going to have a whole hypersurface to deal with, and you can't define a local operator that way. But because of this convenient foliation associated specifically to the presence of the dilatation operator, whose eigenstates we can define on the sphere, we can shrink them back down to go to the center of the sphere and define the operator there. This gives us the state to operator map that we don't have. That we don't have in general quantum field theory. Any questions? Yes.
So is it also an upper cutoff, and after a while you can't act on P and get states?
No, there is no upper cutoff, but it could be that in this procedure, just like this operator, remember we said that there could be operators that are both primaries and descendants, but then you have to set them to 0. That might happen, and in that case, this will stop after a finite number of steps, and only in that case will it stop. Otherwise, it can keep going on forever. But if you hit one of these cases where the quantum numbers of things are such that this is both a primary and a descendant, then you have to set it to 0, and then the whole procedure truncates at that point.
And when delta is not an integer.
Sorry?
When
Delta?
Yeah, it is not an integer. When
Yeah, delta is not necessarily, yeah.
Yeah, so when would it stop by k? Because k always,
Yeah.
I don't know when I would go back to the vacuum.
There will be a state, the primary state in particular, that's what we showed.
Mm-hmm.
So this state over here, if this is the primary state, meaning that it transforms in this way that we showed before, you take that operator, you create a state from that operator using this procedure, right?
Yeah.
That we discussed, this radial quantization picture, then you will be able to show that k on that operator, on that state, is 0. And it doesn't depend on delta. It's not like this delta could be negative. The reason why it terminates is not because it's integer and at some point you get the integer minus itself. That's not why it terminates. It terminates by requirement in some sense. If the theory, if the theory is, say, not unitary, for example, then it doesn't have to terminate. You can allow these dimensions to go all the way to negative infinity. It's fine. But by physical assumption, here, there should be a state, and in unitary theories there turns out to be a state that is annihilated by the operator delta, because there are operators that are annihilated by k, which are these primary operators. And this operator state correspondence tells you that there's going to be such a state.
Maybe a naive question. How do you choose which point in the space-time to be the origin? Because it seems that by choosing a particular point, you are breaking the translation invariance.
Yes. Let's see. So if I define an operator at any point, right, I can move it to any other point by conjugation like this, right? So I haven't broken, just by looking at the operator at a certain point, it's not that I have broken the invariance. I can move the operator to another point, and I will get correlation functions of the operator at the other point, which will behave covariantly with the symmetries that I have in the theory, right? I can, however, choose any particular point I want. It doesn't have to be the origin. Any particular point I want. And define my radial quantization and do this mapping of, the reason why we choose 0 is because when we have an operator and we insert it at the origin, we know that the action of k mu annihilates the operator. So similarly here, we want to create a state that has a similar property on the Hilbert space, which is this delta state that is generated when you insert the operator at the origin. And then any operator you insert not at the origin inside the sphere is fine, you can do that. But then you know that you get an infinite linear combination in general of states associated to that operator on the Hilbert space. But we haven't broken the symmetry in any way, but we've chosen a point where we can easily describe what the symmetry does, and then we can translate to other points using this conjugation. We always do this, right? I mean, you always choose a point that's convenient, you describe things there, and then the rest follows by symmetry. Other questions? Yes?
So if we set it up so you can't build a Bernoulli module over the vacuum, because you're saying P is annihilating your vacuum. I thought normally you do have a way you can start with the vacuum and build up a whole hierarchy of states of it.
So if you insert the identity of, so getting the vacuum on the state, on the Hilbert space, on the sphere, corresponds to inserting the identity operator.
Yeah.
And acting with P mu on the identity operator will give you 0. There are no descendants of the identity, right?
Right, okay.
In order to get states on the Hilbert space, you have to insert a non-trivial operator at the origin. And then P mu on that will not give you 0 anymore.
Okay.
But on the vacuum, it will give you 0. After all, it's a Lorentz invariant theory. If it didn't, then you'd have some sort of preferred vector, and that would not be Lorentz invariant.
But in a 2D CFT, you do build the modules off the vacuum states, don't you? So why do it there? You still act with the Virasoro modes on what you've chosen to be the SL2.
But there you have more. It's not just you don't act. It's not just with the global part. You act with the Virasoro modes.
Yeah.
Not the global part. This P is in the global part. That still remains 0.
I see. Okay.
It's not -1, 1, or 0. You act with the other ones, the other L's. Yeah. And yes, yes. But the global part will still.
Yeah, the global part.
Yeah.
I see.
Yeah.
Okay,
Yeah. Other questions? Yes.
What if we insert like more than one operators? For example, I want to insert 2 operators. One is at X and one is at
This will be, getting products of operators, like how in QFT you get 2 particle states. When you do quantization, you go to momentum space, you interpret things as 1 particle states and 2 particle states. It's exactly the same. You'll get products of local operators, which you can insert at different points. Operator 1 at x1, operator 2 at x2. They will create states in the Hilbert space that are associated with it will be infinite linear combinations of the eigenstates of dilatations in Hilbert space, and they are associated with the product of operators you inserted. They can act,
You can express it via the OP.
I didn't want to say this because we haven't talked about the OP, but next week we'll talk about the OP. Yeah. The product, if you want. What the statement would be, if you had known about the OP, would be that you can take any local any non-local product of operators, meaning bilocal, say, depends on x1 and x2, and decompose it into a sum, infinite perhaps, of local operators, which you can insert either at x1 or x2 or anywhere you want, right? When you do this procedure, now you know how to define the operator. So you can do this the states. And you can do this recursively, and however many operators you have, you will always be able to reduce that using the OP many times. And then the x dependence will go into some C function coefficients that don't act on the Hilbert space. Yes?
So the OP tells us that there are not really any multi-particle states, because everything is just.
It tells you that their effect is to construct different linear combinations of the eigenstates in the Hilbert space. But those different linear combinations are, the x dependence is in them in some sense because it's captured by the C function coefficients, right? The Wilson coefficients of the OP.
Yeah, but I'm saying that the fact that when you have a product of two operators, it's just a sum of
local operators.
Local
Yeah.
operators.
Yeah.
It's like saying that there's not really any two particle state is just a sum of single particles.
Exactly. Yeah. Yeah.
Which is different from QFT.
No, it's also true in QFT. There is an OP in QFT in X space that you can.
But it's not convergent.
Yeah, it's not convergent, so there are issues. And of course, in QFT, you don't describe things in X space anyway. You go to momentum space, and then you define one particle state, two particle states, which how you get because of p mu that you use there. So here it's a little different. And the convergence of the OP will allow you to, talk about things in this way that you do have an OP in QFT, but it's not convergent, so things become, of course, more tricky. Okay. So what do we do now? First of all, we look at how much time we have. Okay. And now I want to talk about, so why did we introduce this radial quantization? It's because we have this, it allows us to have this operator state correspondence that works both ways. So now it becomes very easy for me to talk about things like unitarity, for example, because if I want to talk about unitarity for operators, it's quite tricky, right? I have to define conjugations the right way, and I have to do things rather carefully. But now I have an operator state correspondence, so I can go to the Hilbert space, prove things there, and since I have a correspondence, I can borrow the results and say, oh, they apply also in the operator case. So this is the motivation, or one of the motivations rather. And so even though we might not use it extensively, it's very useful to know what is the conjugate of an operator in radial quantization. Okay, so that's what we want to talk about unitarity here. And in order to talk about unitarity, we have to discuss norms in the Hilbert space. And in particular, we want our theory to only give rise to states whose norms are positive definite. You don't want any negative norms. That would signal a violation of unitarity. So what is the conjugate of an operator in this radial quantization? Now, so we went to this radial quantization, and we want to find the conjugate now. But finding the conjugate is rather easy if you're not in radial quantization. If you are, say, in Minkowski, standard quantization, then you can find the conjugate of the operator rather easily. And here, we don't know what it is. So what are we going to do? Well, we're going to do a trick. Since we have conformal transformations, we can take this, we can map RD to R times SD minus 1. People say we can go from the plane to the cylinder. So this is a mapping from RD to RSD minus 1, which you can do with a conformal transformation. It looks like this. Take your space element, which is dr squared plus, and then we'll write this as ds squared of sd minus 1, and pull an r squared out. Like this. And we will call this e to the 2 tau d tau squared where r is e to the tau. Okay, and now this is r, the real line, times sd minus 1. So we went from r to the d. So let me see if we went from r to the d to r times sd minus 1, and this is done by means of a, but the difference in the two line elements is e to the 2 tau, which is a conformal transformation. Okay? Why did we do this? This redefinition over here, e to the tau, tells us that doing a dilatation in this r, so sending r to lambda times r, right, means in this picture is equivalent to tau going to tau plus log lambda, right? So dilatation here became time shift here, time translation here. Okay? So time translation, we know how to deal with time. We know how to define conjugation when our quantization is that in a time foliation. But now we've done a conformal transformations and transformed our situation from the case of dilatations to one where it looks like time translations. So I can borrow whatever I know from time translations, right, and apply it here, and that will allow me to figure out what conjugation means in radial quantization. Okay, that's the trick. So let's see how you do that. So let's define this cylinder operators. So they're defined on r times sd minus 1 on that cylinder. And let's define them by giving a time on the cylinder and then some normal vector like this. They're related by a conformal transformation to the operators we had in flat space, right? With e to the delta tau, where this tau is the same parameter, and those are at the point e to the tau times the normal vector. Okay, so these are the operators, and in the conjugation in the cylinder, we know what it does. We know what conjugation on the cylinder means, because the cylinder uses this time foliation. So conjugation on the cylinder, and we are in Euclidean, we'll just change the sign of time. Why does it change the sign of time? When you do conjugation in Minkowski, you don't change any signs, right? But here we're in Euclidean, and Minkowski and Euclidean are related by an I. So conjugating, the I will give you the minus sign for the Euclidean time. So this is how conjugation acts in Euclidean, and now I can use this relation, right, to see how it acts in the old operators in radial quantization. So since it will change t, it will change tau to minus tau, so I will pick up a minus sign up here, right? So it will look like I am sort of inverting the position of the operator. So the dagger here is going to be something, we have e to the minus delta tau because of that minus sign over here in this equation. And this will give us, in the end, we will write it as 1 over x to the 2 delta. You can work out the algebra. O flat x mu over x squared. So it becomes an inversion. So the point here is that conjugation in radial quantization is equivalent to an inversion of the position of the operator. Okay? Yeah, it's just
About the second line.
where, here?
Yeah.
Yeah, here. Thank you. Yeah, thank you. So, if you now remember, when we take an operator like this, we proved that conjugation of the operator is an inversion, and the operators in the algebra will be therefore related by conjugation as well. So what I mean by this is that, so first of all, if we have a state psi, then the state psi is given by O acting on the vacuum. Then we can define the state, the bra state, as the vacuum where we act with OX dagger. And O, as we showed here, OX dagger is an inversion on O of X. So this is what we showed. And operators are then conjugated by inversions. And so, if you remember, we knew that there is this relation between K mu and P mu, right? Because we said that K mu sort of fixes infinity and translates, fixes 0 and translates infinity, which is like a translation in inverse space. So you invert, you translate, and then you invert back. And we proved that the action of conjugation is that of an inversion. Since P mu is conjugated by inversions to get K mu, that means that in radial quantization, K mu is P mu dagger. Okay? So this basically allows us to view in radial quantization K mu and P mu as conjugate operators. So P mu will be a raising operator and K mu will be a lowering operator. And just like the A and A dagger operators in the Dirac picture, this K mu at some point will annihilate a state. That state will be the primary state. Acting with P mu on that state, you'll generate all the other states in the Fermat module associated with the operators that you have in the operator picture. And you can define the norms of states now, which we'll do next time. And we'll see how what constraints unitarity puts in the states that you define in radial quantization, which is the easiest way to discuss unitarity. So we went through all this because we want to discuss the constraints that unitarity puts on correlation functions. And to do this, we needed to introduce radial quantization today and understand what conjugation means in radial quantization, so that we can now discuss norms in Hilbert space. And with the state operator correspondence, use the results for the norms in the Hilbert space and translate them to results for the operators. So this is what we're going to do next time. Questions?
Can you repeat this why you wrote that K mu is inversion? This we showed before. Remember, K mu. Remember, we had some differential equation, and then we said, oh, it's hard to, we worked out the infinitesimal form of the transformation, right? And then we had to work out those integral curves of the transformation to find the finite form of the transformation. And then we had some differential equation, and I said, well, do the transformation y mu goes to x mu over x squared. That differential equation, which was complicated, became that of translations in the new variables, but this is an inversion. So I solve the translation in the new variable in inverted space. Then I have to come back in real space, so I have to invert again. So this is that relation. In radial quantization, this becomes just conjugation.
Okay. And let's talk about the rest next time then. Not all the rest, but there are 2 more lectures. So some of the rest. Yeah.
Okay.